We'll just start after a few minutes. I'm waiting for others to join. We'll just start after a couple of minutes. So instructions remain the same. So, in case of any doubts and queries, you can type it in the chat box. If you are not able to ask your doubt in the chat box, you can use your mic, but give the preference to chat box only. So we'll just start with, I think after 1 minute we can start. Okay, so we can start. Let me just share my screen first. Good afternoon, everyone. My name is Musa Rafi. I'm a PhD student at Department of Electrical Engineering at IIT Kanpur. So I'm your course TA for this course, Digital Circuits, which is taught by Professor Shantanu Chattopadhyay of IIT Kharagpur. So in this session, we'll be discussing problems related to week 7 material. Hope this live session will help you with your assignments and all the questions pertaining to this week. So I'll just first admit some students, then we can proceed with the presentation. So to those guys who have joined in late, let me just give introduction once again and also give out the instructions for today's live session. My name is Musa Rafiq. I'm your course TA and this is the course on digital circuits. In this session, we'll be discussing problems related to week 7 tutorial. And also regarding this live session, after every question is solved, a couple of minutes will be given to asking your doubts. If you have any queries or doubts regarding a particular problem, you can just type it in the chat box. If you are not comfortable with the chat box, then you can use your mic and ask in your doubts turn-wise. So let me just admit some students and we can proceed with the first problem. Then I will admit next batch of students only after the particular problem is solved. So let me just go to the slideshow mode and let's start with the first question of today's live session. So the first question is this: what is the output signal frequency for the following circuit with 5 megahertz clock signal? As you can see, this is we are giving this flip flop. If you carefully examine it, it is a T flip flop made up of the D flip flop. So we know that for a T flip flop, when the input is 1, when the input is 1, we have a toggling occurring at the output. So if the input, this is Q plus, so this will be Q bar. So output will be just complement of the previous state output. So here we have this, we are asked what is the output signal frequency for the following circuit. So input clock frequency is 5 megahertz, and this is a positive edge triggered flip flop. So let me just draw for this a waveform like this. This is for the clock. No, no, this is not the. This is for the clock. And one more thing I would like to point out. See, this input will always be equal to 1. If you carefully examine this, t is always equal to b1, so toggling will happen always. And once toggling will happen, toggling will only happen at the positive edge. So we will see that on positive edge, if initially q was equal to 0, if initially q was equal to 0, toggling would occur at the positive edge, or like on this, then this, and then this. So just like we did the last week, so the f output will be equal to f clock divided by 2. So f output will be equal to 2.5 megahertz. But this condition is satisfied only when t is equal to 1. So we have this answer: f is equal to 2.5 megahertz for t equal to 1. Frequency gets divided by 2. So the answer to this question, which states that what is output signal frequency for the following circuit with 5 megahertz clock signal, is 5 by 2, that is 2.5 megahertz for t equal to 1. Let me just admit some students, and also if you have some doubts, please type it in the chat box. I guess there are no doubts regarding this question. We can proceed to question number 2, if that's fine with you. Okay, I can't see any doubts, so let me just move towards the question number 2. Question number 2, someone has joined in. Let me just admit the person. So let me just start with the question number 2. So question number 2 asks us what is the modulus value of 5-bit ring counter. So here, let me just point out the things. Here we have this. We have to find out the modulus value of 5-bit ring counter. Key here is this ring counter statement. If it would have been in synchronous counter and 5-bit, we would have stated that it would be the number of mod value would have been 2 to the power 5. But for a ring counter, the mod value for a ring counter, mod value, which we write it as mod n, this n is equal to the number of flip flops. And since it's a 5-bit ring counter, for a 5-bit ring counter, the number of flip flops will be, for a 5-bit ring counter, the number of flip flops will be 5. So the modulus value of the 5-bit ring counter is simply 5. Mod n is equal to number of flip flops, that is equal to 5. So the correct answer to this question is 5. No, this is not also called Johnson's counter. No, Johnson's counter is twisted ring counter. Vimala Musti, Johnson's counter, we call it as a twisted ring counter. Ring counter is different. I have typed in it on the chat box. Twisted ring counter is equal to Johnson counter. So I guess we can move forward to the next problem. That is question number 3 of today's live session. So let me just start the slideshow. So the question number 3 asks us to write the contents of the following registers. Just first write the contents of the following registers: Q4, Q3, Q2, Q1, Q0 for 3 clock transitions. Assume the initial values of all flip flops are logic 1. So we are given this circuit which consists of this D flip flop. Someone has joined in. Let me just first admit them. Try to be on time. Although recordings are available, but still try to be on time. It will help you. So I'll just read out the question again. Write the contents of the following register Q3, Q2, Q10 for 3 clock transitions. Assume the initial values of all flip flops are logic 1. So these are just D flip flops. This is a clock into all the flip flops, and this is the output of the Q4 connector with this XOR gate with this Q1 also, and given to the input of this flip flop. So we are required to write the contents of the following register for 3 clock transitions. So let me just first draw the truth table. No state diagram. I can't see it. Truth table. Let me just call this table. So this is clock. Then we have this Q4, Q3, Q2, Q1, and Q0. When there was no initial state, we'll just state initial state. The condition given is that all the values of the flip flop are at logic 1. So these all will be 1. Now at the first clock cycle. So at the first clock cycle, this Q4 which was 1 is going to this XOR gate, and this Q1 which was also 1 is going to this XOR gate. So this D is 0. So D to the 0 is 0, so the output will be 0. And this Q0 was 1, so it will be 1. This was also 1, it will be 1. This was also 1, it will be 1. And this was also 1, it will be 1. This is after first clock transition. Now for second clock transition, this Q4 is again 1 and this Q1 is also 1. So this D will be again equal to 0. So Q0 is equal to 0. Since the Q1 in the previous cycle was uh, Z, Q0 in the previous cycle was 0, so Q1 will here be equal to 0. So let me just write, I can't find my cursor, yeah. So this will be 0, this will be 1, and this will be 1, and this will be 1. Now for the final clock transition, that's the third in this question, Q4 is Q4 is 1 and Q1 is 0. So its XOR gate equal to 1. So Q0 will be equal to 1. Q0 was previously 0, so it will be 1. Q1 was previously 0, so it will be 0. And these two will be 1. So these are the contents of the register for 3 clock transitions. So let me just repeat. I wrote this clock Q4, Q3, Q2, Q1, Q0. This is the first initial state at which all of the flip flops were contents were equal to 1 at logic 1. For the first clock transition, this Q4 was 1 and this Q1 was also 1. The input would be 0. And then it will be 1, 1, 1 for all flip flops. Then for second, similarly like this. And for the third, where the input of the XOR gate was 1 and 0. And D0 will be equal to 1, so it was 1. This should be 0 here, sorry, this should be 0 here. This is 0 here. And 1, 0, 0, and this will be 1 and 1. So this is the contents of the register for 3 clock transitions. See, Vimala, you have written the answers in the format Q0, Q1, Q2, Q3, and Q4. Your MSB is Q0 here. Try, you have to keep hold of these things. Your answers are right, but in reverse order. Try to write in this formula, in this form. Q4, Q3, Q2, Q1, Q0. If you check your answers, it's the first bit is Q0. Although it's I can understand this answers are correct, but whatever the question is asking, write in that format. I hope you got my point. Any other doubts regarding this question? So if there are no further doubts with this question, we can move forward to the question number 4. Question number 4 asks us which of the following output sequence Q2, Q1, Q0. See, again, I'll just mention Q2 first, Q1, Q0. Q2 is our MSB and Q0 is our LSB. Q2, Q1, Q0 will be produced by the following circuit. All flip flops are negative edge triggered. So before we start, let me just first draw the clock, waveform for the clock. and these are negative edge triggered, so I'll just mark the negative edge only. And see here, this clock goes to this T flip-flop, which is Q0. So I'll just mark this Q0. So here, since the question has not given anything regarding the initial states, let's just first assume that all the states were equal to 0, 0, 0. So this was equal to 0. So at the negative edge triggered, since all the t's are equal to 1, toggling will happen. So if this Q0 was 0, at the negative edge of the clock, this will toggle, and then the state will remain same until it finds another negative edge. Then again the state will toggle once it finds a negative edge, and then this. Now this Q0, which I'll mark the negative edges for this Q0. This Q0 acts as a clock for this T flip-flop, that is number 1. This was 0, this was 1, and this was 2. So let's just we had made an assumption that all the flip-flops are in the 0, 0, 0 state. So it was in the 0, 0 state, the toggling will happen only at the negative edge. So like this. So this is the negative edge for this. Now this Q1 goes to the clock for this number 2. So toggling will happen, and we assume that Q0 was equal to Q2 was equal to 0 initially. Toggling will happen only at this state. So if me just let me just draw these dashed lines at the negative edges of the clock. So initially it was 0, 0, 0. Then it was 1, 0, 0. Then it was 0, 1, 0. And then it was 1, 1, 0. 1, 1, 0? Yeah, 1, 1, 0. So my states are Q2 makes a transition. See, Q2 I have to write it like this: Q2, Q1, Q0. It is 0, 0, 0. Then it goes from 0, 0, 1. Then it goes from 0, 1, 0. And then it goes from 0, 1, 1. So these are my states. If you carefully look at the options, this is option number 0, 0, 0 and 0, 0, 0. 0, 0, 1. This is option number A. So option A is our correct answer. And also I would like to point out one thing here. If we had made an initial assumption that Q2, Q1 and Q0 will have been 1, 1, 1, then we should also evaluate that case. So what happens at that case? Since we have to check that case also, I'll just show it quickly here. So clock is here. If it would have been 1, 1, 1, so this is minded. This is I'm showing for if I assume initial states for 1, 1, 1. I'll just make a new slide for that. Let me just here I can draw it here. So this is for if initial states are 1, 1, 1, because we have to check that thing also. So if it was 1, this is clock, this is Q0. If it was 1, it will go to 0 here, then it will go to 1 here, then it will go to 0 here, and then it will go to 1 here. So these are the negative edges for this. Then Q1, if it was 1 initially, it will go to 0 here, then it will go to 1 here, and then it will go to this. Then Q2, if it was 1, then it will stay at 0. So it was 1, 1, 1, then it was 0, 0, 0, and then it was this is 1, 0, 0, and it is 0, 1, 0. So 0, 0, 0, 0, 0, 1, 0, 1, sorry, 1, 1, 1, 0, 0, 0, 0, 0, 1, and 0, 1, 0. So none of the options is like this. So we can just confirm it as this is our correct answer. If this option was also given, then it would have been like 2 answers would have been there. But since it's not given, we can just assume that we can just write our option A is our correct answer. This is a case where we had assumed our initial states are 1, 1, 1. So in case of any doubts and queries regarding this question, please type it in the chat box. Vimla, why you have written C? Okay, okay. I hope you got the. So, any other doubts? So, if not, we can move forward to this question number 5. I guess 5, yeah, 5. So, the question number 5 asks us the minimum number of flip flops required to design a mod 150 counter. So, mod 150. So, we know this mod n should be less or equal to 2 to power n, where n is the number of flip flops. Small n is the number of flip flops. So here we are giving this mod 150. So 150 should be less or equal to 2 to power n. So let's just say n equal to 7. So for n equal to 7, I think 32, 65, 61, 128. And for 2 to power 8, 7 is equal to 128. So 128 is not less than 128 is not greater than 150. So n is not equal to 7. So our next choice is n equal to 8. For n equal to 8, 2 to power 8 is equal to 256, and 150 is less or equal to 256. So the minimum number of flip flops required to implement a mod 150 counter is equal to 8. So option A is our correct answer. So the minimum number of flip flops required to design a mod 150 counter is 8. So we can proceed to the next problem. The next question states this. Okay. Okay. So the next question asks us, what is the output sequence of the following circuit after 5 clock transitions? So we are just asked to write the what is the output sequence. So mind this QA, QB, QC, QD in this order of the following circuit after 5 clock transitions. Assume initial state of all the flip flops is 0. So here we have this T flip flops, clock given to all the flip flops is positive edge triggered, and we have this reset signal, and we have this Q bar connected to this T flip flop. So we can just write it here. Clock. No, let me just write it down because then this picture and picture point camera comes in there. So this is QA, QB, QC, and QD. And clock is not first initial state. So what are we given? All the flip flops are in 000 state. Now at the first clock instance, change will occur only at this thing, QA. No, at all. Why am I saying QA? Clock is given to all. So at this instant, change will occur here. So Q bar, this Q bar, which was base 1, is acts as input to this. So this QA will toggle. So it will be 0. And for all the other cases where they were only 0, so they will remain at Q their previous state. So 1, 0, 0. Now at second instance, this Q bar is still equal to 1 and connected to this T flip flop. So let me just at the second, so it will again toggle, so it will be 0, and this Q1 was equal to this input to this T flip flop, it will toggle, so it will become this 1, then it will remain as 0, 0. So this was second transition. Now third, fourth, and now this Q1 is again equal to 1, so Q bar is again equal to 1, so it will again toggle, it will go to 1, it will go to 1, and this is 0. This input to this flip-flop is 0, so it will remain at its previous state. This will toggle because input is now 1, it will go to 1 and it will be 0. Then again this will toggle, it will go to 0. This will toggle, it will go to 0. This will also toggle, it will go to 0. Now this thing will toggle, it will go to 1. Now this is 1 minded, and q, this is for this, so q bar will be 0, so it will remain at this previous state, and it will also remain at the previous state, it will also remain at the previous state, and it will also remain at the previous state. So after 5 clock transitions, our output sequence is 0 0 0 1, qa, qb, qc, qd, in this order, not qd, qc, qb, qa, qa, qb, qc, qd. That's what question asks us. So it is 0 0 0 1. So the correct answer is option A. Any doubts regarding this question, please type it in. Clock is similar to all push, given to same. So this is a synchronous flip-flop. So same thing will occur at all instances. Yeah, it's positive edge trigger. If you just carefully look at the circuit. So if there are no further doubts, we can proceed to question number 7, I guess. Question number 7. Okay. So which of the state diagram represents the following circuit? So what is this circuit? Let's just first examine this circuit. So this is the D flip flop. We just draw a D flip flop here, and then we have a mux. So we know that the D flip flop outputs whatever its input. So D equal to Q equal to D simply. So this is a select line. So let us first draw like this: Q equal to 0 and Q equal to 1. So let's just consider Q is equal to 0. So if Q is equal to 0, this thing is 0. And for select line, there are two possibilities: A equal to 0 and A equal to 1. So when A is equal to 0, this line will get selected. And when A equal to 1, this line will be selected, and Ry will be equal to D. So Ry equal to Q. So for A equal to 1, our output will be equal to Q only. So this is A equal to 1. So this is A equal to 1. Now let's check what will happen at A equal to 0. So when A equal to 0, the complement of Q gets selected. So when A equal to 0, this select line gets selected. So Y is equal to complement of Q. So this thing changes. A equal to 0. And when A equal to 0, this thing changes. So let's just look at it here again. So let's just say this is Q and this is Q. So when A equal to 1, this Q gets selected, and when A equal to 0, the complement of that thing gets selected. So it makes a transitions for when select line is 0, and it remains at the same position when A equal to 1. So if you just carefully look at the options, this is a, so this is option D. So the correct option for this question is option D. Okay, let me just explain again. So what we are given is we are given this mux. So let's just first examine this mux. So when A is equal to 1, x1 will be selected. That is Q is output. So if it was at Q, it will remain at Q. When A is equal to 1, 0, this line will be selected. So Q bar. So if it was at Q, output will go to Q bar. So that's the whole thing I have drawn here. This. When Q is equal to 0, and A is equal to 0, output will be Q equal to 0, simply. And when A is equal to 0, output will be Q bar. So Q equal to 0, so output will be equal to Q equal to 1. It will go to this state at A equal to 1, A equal to 0, sorry, because this select line is selected. Similarly, for this case, when Q equal to 1 and A equal to 1, output will be equal to Q equal to 1 only. And when A equal to 0, it will make Q bar will be selected because X0 is selected. It will make a transition to this because it's complement of this. So this is option D. I hope you got this. Now let's just move towards question number, I think 8. This. So question number 8 asks us, which of the following statement is true? A is output of millisircuit depends on current input only. Output of millisircuit depends on current input and current state of circuit. Moore machine output depends on current input value and none of the above. So you must be knowing that the milli machine, the output of the millisircuits depend on current input and current state of the circuit. And for a Moore machine, output depends on current state, not current input. So this is a simple theoretical question. I hope you'll be well versed with this concept of milli and Moore machine. And the correct answer to this question is option B. Millisircuits are, let me just, millisircuits are those circuits, basically a sequential circuit in which the output is depend on the current input and the state of the input. You can just say it as a combinational circuit with some memory, where the whole output will depend on the current state of the input and whatever the state it was in, not only the state of the inputs. But in the Moore machine, it's depend on the state, its memory, not on the inputs. So you can just refer to the lectures to get more acquainted with this. Yeah. Has this been taught in week 7, by the way? Yeah, I think it's taught. I saw it. So let's just move to question number 9. So what is the modulus value of 5-bit Johnson counter? So earlier we had this, if you remember in the earlier question. Am I audible? Can someone just confirm it? Okay. So earlier we had this mod n for a ring counter. You saw it in one of the earlier questions. And we said that the number of states in a ring counter are equal to the number of flip-flops, and it was n. But here we have a Johnson counter, which is also known as toasted ring counter. And for a Johnson counter, mod n is equal to twice the number of flip-flops. And the number of flip-flops is simply the number of bit value here. So it is 2 into 5. So for a Johnson counter, of a 5-bit Johnson counter, the modulus value is simply 10. 5 multiplied by 2 equal to 10. If it was a ring counter, it would have been equal to 5. But in Johnson counter, the value is twice the number of flip-flops, that is 2 into 5, that is 10. So the correct answer to this question is option B. Yeah, see, the final output is connected to the input in case of a ring counter, and in case of a Johnson counter, the complement is connected to the input of the first counter, this flip-flop. That's the difference, and that thing increases number of states. See, this is a ring counter where this thing is connected to this, and in case of a Johnson counter, Q bar is connected to the input. So someone has joined the meeting. Let me just admit the person. Anil, it is 10. I hope you got the explanation. So let's just move to the next question. It states that the current state of two JK flip-flop QA and QB system is Q00. Identify the sequence produced by QABB. So we just assume that the initial, no, we won't assume, it's given initial state is 0 0. So this is the, and this JK of the first flip flop, I'll call this as first and I'll call this as second, is connected to high voltage. So J and K equal to 1, so it will toggle. This thing will always toggle. Keep that thing in mind. At the positive edges of the clock, this thing will toggle because the input combination is 1 1. So this is clock, and this is my QA, and this thing is my QB. So initial state, I'll just write down it as 0 and 0. So when the first clock instance is there, this thing was 0 and this was 1 1, so it will toggle. QA will be equal to 1. So since the for a second flip flop, the clock is connected to this complement of this, so it will be 1. So, no, clock, no, not clock, input are connected to complement of this. So this was 0, so this was 0 and this is 1, so this is J equal to K equal to 1, so this thing will toggle. So out QB will be 1 1. Now coming to the next clock cycle, this is 1 1, this thing will again toggle, and this thing was 1 and this will be 0, so J and K equal to 0. We know this, for a J equal to K equal to 0 combination, the output is the previous state in output, so it will be 1. Now the next combination is 0 0. This thing will toggle always, mind it, QA will always toggle because J equal to K equal to 1 at clock instances, it will always toggle, so it will be 1. So this was 1 previously, this was 0 previously, this is 1, so this thing will toggle, so it will be 0, and this will be 0, this will remain at 0. So we came back to the same state and this thing will repeat. So what are my sequence order? QA and QB. QA is my MSB and QB is RSB. So 0 0 1 1 followed by 0 1, then 1 0 and 0 0. 0 0 1 1 1 1 0 1 1 0 0 0, and this thing will repeat 1 1. So let me just check the options. This is option 0 0 1 1 0 1 1 0 0 0 1 1. This is option C. Let me just repeat this again. So we are giving these two JK flip flops 1 and 2. J and K are always high, and the input to this is QA complement for this flip flop. So initially these are 0 0. At first instance this will toggle, and this was 1, so this will be 1 1. It will also toggle. Now this will toggle, it becomes 0. So this was 0, this is J equal to K equal to 0, it will remain at 1 only. So using these things in continuum, we get the states. If you have any doubts regarding this, please type it in the chat box. There. Otherwise, we can move forward to the next problem. Yeah, I guess some of you have done it already. Okay, Anil. Okay, you thought it was 4-bit. Okay, that's fine. So question number 10 is done. We can just move towards question number 11. So the question number 11 asks us, consider the following circuit shown in the figure below. So this is a T flip flop. T flip flop is there. Sorry for my drawing. Let me just draw it again. A T flip flop is given where the two outputs Q and Q complement are given to XOR gate. So this will always be equal to 1, and when this T is equal to 1, there will be toggling. You know that for T equal to 1, Q is equal to Q bar. So we'll get a frequency divider. So it is the input clock. So positive edge triggered. Output will be like this. If it was 0, it will go like this, this. So F output will be equal to F clock by 2, and F clock was 10, so it is 10 by 2, it is 5 kilohertz. So option B is our correct answer. I guess we have done a lot of questions in this pattern. I'll just move forward to the next question quickly. So the question number 12. So this is 12, yeah. Question number 12 is based on this finite state machines. It asks us, what is the output and state of circuit represented using row state diagram for input sequence 1 1 1? and we are giving this that initially the circuit is in state A. So when this circuit was in state A, this is our reference circuit. So we are in state A. So what is our input? 1. So input 1 will go to state B with output equal to 0. Then we are again in state B and our input sequence is 1. So we'll go to C as per the given diagram. We'll go to C and our output is 0. Now this one is also done. Now we have third one. So as per the state diagram, if we are at C and our input is equal to 1, we will be remain at C with output equal to 0. This thing. So if we follow the sequence, we are like this: 1 0 1 0 and 1 0. So we are at the state equal to C and our logic value is equal to 0. So the correct answer is option C. No, option C. Yeah, option C. Logic 0 and the state is C. If there are any doubts regarding the question, please type it in. Yeah, I guess some of you have already solved it. That's nice. So this was question number 12. Now moving forward to question number 13. Okay, Vivek, you want me to repeat it? Sure. Which circuit? This is the state diagram. This represents the circuit. The state diagram itself represents the circuit, whatever is happening here. So I'll just repeat it for Vivek. He has asked me to repeat it. So Vivek, the question asks us what, and for all the what, find the output in the state of the circuit represented by the following state diagram for input sequence 1 1 1. So given it as we are at state 1, state A. So I am at state A, and my sequence is 1. So these first, you see this order representing this like A by B something. A represents your input and B represents your output. So right now I'm state A and my input is 1, so I'll go at state B with output equal to 0. Now I'm out at B. Now as per the question, I am following 1 1 1 sequence. So 1 is done. Now I'm again at now I'm at B and my input is again at 1 is 1. And so what happens after the state diagram? I go to C with output equal to 0. Now as per the question, now we have one more input given to the circuit. So I'll be at state C. See, I'll be at state C, and as per the state diagram, if my input is 1, I'll remain at state C with output being 0. So my output is 0 and my state is C. That's what I have done here. I hope I'm clear. Vivek, can you just confirm? Okay. Now moving forward to question number 13. 13 asks us the circuit consists of two clock JK flip-flops connected as follows. The output J equal J0 Q0 is equal to Q1, and J1 Q1 is equal to J0 Q0 is equal to Q1, and J1 Q1 equal to Q0. Each flip-flop receives the clock simultaneously. The input of the circuit acts as. So let me just write down the state diagram. So this is my present state. I think there is a mistake here. It should be J. I'll just write the new conditions. J1 equal to J1 is equal to Q0. Ignore this thing. J1 is equal to Q0 and J0 is equal to Q1 bar. Then we have K1 is equal to Q0 bar and K1 also K0 also equal to Q0 bar. There's a mistake there. Take this condition. So I'll just draw the this represents my present state. which is Q1, this output of one JK flip flop, and Q0 output of another JK flip flop. Then I have my input combinations J1 K1. J1 is equal to Q0 and K1 is equal to Q0 bar, Q0 bar. Then I have my another inputs as J0 equal to Q1 bar and K0 equal to Q1 bar, and these are my finally I'll be having next states, that is Q1 plus and Q0 plus. Let's just assume that initially they were 0 0, so Q0 will be 0 and Q0 bar will be 1. Q1 bar will be 1 and Q1 bar will be 1. So J0 K0 toggling will happen. So if it was Q0 was 0, this will be 1, and this is J1 0 1, it will remain at 0. Now my next state input will become present state input for the next cycle. So Q0 is 1 and Q0 bar is 0. Q1 bar is 1 and Q1 bar is 1. So this is 1 0, 1 0 for J1 Q1, it will become as 1. And for J0 Q0 it is 1 1, toggling will happen and it becomes 0. So it is 1 0. My 1 0 next state outputs will become present state inputs. So Q0 will be 0 and Q0 bar will be 1. Q1 bar will be 0 and Q1 bar will be 0. So for this it will remain as like it is 0 1. So it will go like 0, and since it is 0 0, it will remain at 0. So now I'm again back to this. So what is happening if I was at 0 0, then I am going to 0 1, and then I am going to 1 0, and then back to 0 0. So there are three states, 1 2 3, 1 2 3. So I am making transition from 0 0 to 0 1 and then 1 0, then back to 0 0. So if you can see this, this is 0 1 2, then back to 0. Three states, so this is counter of mod 3. Yeah, I think there are some questions. Yes, someone has turned on his mic. Kindly keep it on mute. Shankar, I'll repeat. So one thing, keep it in mind. Ignore this thing. Remember this thing. There's some typing mistake. I'll just check it again. But your input combinations are like this: J1 is equal to K0, J0 is equal to K1 bar, Q1 bar, K1 is equal to Q0 bar, and Q0 is equal to Q0 bar. So initially present state are like 0 0, and my inputs are J1 K1 and J0 K0, and as per the combination Q0 and Q0 bar, let me just highlight it. This is Q0 bar. So it was 0 0, so it will become Q0 is 0 and Q0 bar become 1, and Q1 bar and Q1 bar will be 1 1. So for flip flop number 1, for flip flop number 0, toggling will happen, so it will become 1, and for Q1 it will remain at Q1, that is 0. Then 0 1 will become my next present states, and my J1 and K1 will be 1 0 as per this combination, and my J0 and K0 will be 1 1. So for 1 1 toggling will happen. So if it was 1, it will become 0. That's what happened. And for 1 0, it will be set, so it will become 1 0. Now my 1 0 will become the present state of this. And J1 K1 are 0 1 and J0 K0 are 0 0. So 0 0 means the state remains same, so it is 0. And 0 1 is 0 simply as per the logic of GK flip flop. So then I have 0 0 and it again go back to this. So I am having three states: 0 0 0 1 1 0. So it is a mod 3 counter. Here, where this is next state, this is Q1 plus and Q0 plus. So Q1 plus and Q0 plus. This is 0 1 1 0 and 0 0. And now it's clear. So let me just move forward to the next question. That is question number 14. So if the following counter is initially set at 000, then straight after the 6 clock ABCD will be ABCD. We have to find the state of the state after 6 clock transition. So initially it was this clock, then we have this clock, this is A, B, C and D. So this was not allowed, so it was 0 0 0 and 0. And at the rising, so this D bar will go to this will become 1 and all zeros will propagate further. Then at the next clock, this one will go here and this one will go here. It will be 1 1 0 0. Then this will happen again 1 1 1 0. And this is my fourth clock cycle. It will be 1 1 1 and 1. Now what will happen? Now D bar will become 0. It will go to 0. So it will be, I'm writing the next two clock cycles here. I'm writing it here. So what will happen? This one D bar will be 0. So it will be 0 1 1 1. And then again it is 0, so it will be 0 0 1 1. So my clock this state will be 0 0 1 1. If you can take a look, so initially it was 0 0 0, D bar was 1, so this D bar will be here and this will become 1 0 0 0. Then it will be again 1, then it will become 1 1 0 0. Then it will again be 1 1 1 0, and then be 1 1 1. And when it's 1 1 1, it will become 0, so it will become input to the first flip-flop will become 0 and then it will be like this. So to add to the point, this is simply a Johnson counter. So after 6 clock transitions, my output will be 0 0 1 1. Now move forward to the question number 15. This was asked in GATE 2020. I happened to sit in that exam, so that's why I picked it. It was a pretty easy question. So the question asks, as the state diagram of a sequence detector is shown below, state S0 is the initial state of the sequence detector. If the output is 1, then output 1 is simply means the sequence has been detected. So we'll follow the forward propagating arrows. So we are at S0, S0. So S0 forward, it goes like this. So when it goes forward, when the input is 0. Then we are at S1. S1 moves forward when input is 1, correct? Then we are at S2. S2 moves forward when the input is 0, correct? S3. And S3 moves to S4 once input is 1. This was S2 to S3 was 0 and this was 1. Now at S3, S3, S3 and I am going to S4. Once I am at S4, once I get input equal to 1, I'll go back to S0, so there is no sequence detection. But once I am at S4 and I get a 0, a sequence is detected by this output equal to 1. So what happens? I go back to S3 at input equal to 0. So the sequence I detect is 0, 1, 0, 1, 0. So if my inputs were like this, 0 1 0 1 0, my output would be like this: 0 0 0 0, and once this 0 occurs at the input, my output will go as 1. So it detects this sequence: 0 1 0 1 0. Follow the forward propagating arrows and see where the output goes to 1, and check whether the output goes to 1 at that sequence. So this sequence is followed: 0 1 0 1 0. Now to the last question of the today's lecture or today's session. The following state diagram which represents which of the input equation given dA equal to AXY, where dA denotes a D flip flop with output A and X and Y are inputs to the circuits. So dA is having A as output. So we'll just draw the characteristic table. We have this A, then we have the inputs X and Y. So total 8 combinations are possible: 0 0 0 0 1 0 1 1, 1, 0, 1, 1, 1, 2, 0. Let's make some this. Let me just draw it here neatly. 0, 0, 1, 1. This is my input to the D flip flop. This is my state of the output of the D flip flop. 1, 1. So let's just take a look at this. So my present state is 0, and when my input combination is 0, 0, where I go. So I'm at 0, and my input state is and my input combination is 0, 0. I stay at 0. So A plus is 0. Refer to the state diagram. So A equal to 0, and my input combination is 0, 0. I stay at 0. So then again my A is equal to 0 and my xy equal to 0, 1. I go to A equal to 1. Similarly for 1, 0 and 1, 1, I go to A equal to 1 and I go to A equal to 1. Now I'm at state 1. State 1. And my input combination is 0, 0. I stay at 1. Now I'm at state 1. My input combination is 1, 0, 1. I stay at 1. Now I'm at input 1 and my state combination is 1, 0. I go to 0. And my input present state is 1. That is A equal to 1. And my input combination is 1, 1. I stay at 1. So this is my characteristic table. Now just drawing the K map for a 3 variable system. 1, 2, 3, like this. Here we have this A bar, and this is A. This is X, Y, 0, 0, 0, 1. X bar, Y bar. This is X bar, Y. This is X, Y, and this is 0, 0, 0, 1, 1, 0. So apart from this 1 and 1, these two are 0. So we can make a chord out of this, and we can make a pair out of this, and we can make a pair out of this. So the term coming out from chord is A is changing and X is changing, so Y. So the term coming out from chord is Y plus this, not taking this pair. This is A bar and Y is changing, this is A bar X. Not taking this pair. This is A, Y changing, and this is X bar. So my final equation is dA is equal to Y plus A bar X plus AX bar. So if you carefully look at this is an XOR gate. So dA is equal to Y plus A XOR X. So my answer is Y plus A XOR X. Y plus A XOR X. So option 3 is my correct answer. So that was all for today's live session. If you had any doubts, please type it in the chat box. Otherwise, we can close today's session. Yeah, sure. By the way, recordings and material are always available. You can just refer to them at any your convenience. So we have to just find the sequence detector. Sequence detector, this is a circuit of sequence detector. So it will hit whenever the sequence has been detected. So right now item as 0 as per the given question. And I am moving forward. So whenever you have been asked to check the sequence detector, check the forward moving arrows. So when item S0, I move forward on 0, then to S1. Then I again move forward from S1 to S2 at 1. then S2 to S3 at 0, and then S3 to S4 at 1. Now there are two forward moving arrows, but from S4 to S3, when I hit this 0 as input, I hit my output as 1. So for a sequence of 0, 1, 0, 1, 0, my output will be 1, and so my sequence will be 0, 1, 0, 1, 0. Simply. You can just refer to this input. So when 0, my output is 0. When input 1, then my output is 0. When 0, then 0. Then 1, then 0. And once the sequence is completed, I'll just hit 1. So my sequence detector will be 0, 1, 0, 1, 0. I hope I was clear. So it's 4:01. We are already going great. But still, if you have any doubts, please type in. So you are enlisted in this NPTEL program now. Yeah, so they'll be sharing every week the video links and the link to the Google Drive. I think it's already present in there. If you can check in your this web page of the portal, it's already present in there. So live this live video lecture live session recordings and PPTs are always available there. So for today's lecture, I guess they will upload it maybe till tomorrow, but you will get them soon. So that was all for today's lecture. Thank you.